So welcome. In this session, we are going to define a vector space. So definition. So vector space. So first we'll start by defining a space. So definition of space. So a set of elements of which certain well-defined mathematical operations are valid. So well-defined mathematical operations are well-defined, remains valid. And then these elements may be functions, vectors, polynomials, matrices, etc. So that's what we call a space. And therefore, once we understand the definition of a space, then we can now define a vector space. So let V be a set on which two operations, that's vector addition and scalar multiplication, are defined. Let U, V, and W be vectors in V, and let C and D be scalars. If all the following properties are satisfied by V, then V is a vector space. So 1, U plus V is a vector in this set capital V. So this is called closure property for addition. That when you pick any vectors in this set V, you add them, then you'll also get another vector in the same set V. Closure property for addition. So that's property number 1. Number 2, U plus V is the same as V plus U. This is called commutative property for addition. And then number 3, U plus V plus W equals to U plus V plus W. So when you change the position of brackets, this property is called associative property for addition. Number 4, they exist an element 0 vector which is in this set V such that if I take U, I add to this 0 vector, I get U. So where I remember U is a vector in this capital V. So this is called additive identity. Property. And then number 5, for all vectors U in V, they exist a vector minus B minus U in V such that if I take U, I add to minus U, then I get a 0 vector. So this minus U is called the additive inverse. So that's the additive inverse property. And then if I pick any scalar, I multiply by any vector U I still get another vector within this bigger set V. So 6C times U is always a vector in V for all vectors U picked from this V. This one is called closure under scalar multiplication. And then number 7, if I pick a scalar, I multiply by the sum of two vectors U and V, then the same as CU plus CV. This is called distributive property. And then number 8, if I take the sum of two scalars, I multiply by a vector U, then the same as CU plus DU. So this is called still distributive property. And second class property, number 9, if I take C, I multiply by DU, the same as C times D, you multiply by U. This is associative property for scalar multiplication. This scalar multiplication. And then number 10, if I take 1, multiply by vector U, I still get vector U. So this is called scalar identity. So this is the end of definition of a vector space. So to define a vector space, then you have to list these 10 properties. And just as a note, so 1, a vector space is defined by 4 quantities. For entities, so these entities are a set of vectors number 2, a set of scalars. And then addition operation. And then we have scalar multiplication operation. So that's one. So therefore, you have to ensure that all these things can be clearly understood if you're defining for vector space. And then number two, when you refer to a vector space V, be sure that all the four entities above are well or are clearly understood. Clearly stated or understood. And then lastly, number three, unless otherwise stated, assume that the set of scalars is a set of real numbers. So the next session will be giving examples of vector spaces and then giving some proofs that the examples will be stating are indeed vector spaces by proving that they all obey the 10 axioms that we have stated in the definition of a vector space. So thank you.